And it's great. And I want to thank the previous panelists who really set up the conversation wonderfully in terms of the incredible ability to see greenhouse gas emissions from space. And Christian did a great job of teeing up the problem and the amazing progress we've made, as well as with Copernicus and Sentinel-5P. We're now able to see so much more from space than we could before. But we can't, as Christian said, we can't see everything we need. We've made a lot of progress, and so MethaneSat was designed and is being built to try and help fill the gap of what we can do now and what we think we need to move forward. And so as we think about this issue, I would just want to reiterate what Dagmar said at the beginning, is that we recognize that methane is the second largest source of warming from human emissions of greenhouse gases. It accounts for greater than 25% of current warming that we're experiencing. And if we really don't take the action that we need to, it could add 1 degree Celsius in warming by 2100. So it's a big player, and it's really important to remember that because it's a short-lived climate pollutant, it is really the most powerful tool we have in the near term to reduce warming. That's not a substitute for the critical reductions in CO2. It's very much we have to do two things, but we need to think about them as two parallel sets of actions if we're going to realize our goals of reducing the damages we're seeing from climate change already and not allowing them to be far greater than currently. So if we, sorry, I need to move. So we, as I mentioned, we designed the MethaneSat mission in order to motivate both countries and companies to reduce methane pollution by giving them the quality of data. And Kairos is doing a great job in starting that and doing a lot of work. We're much further along than when we started this mission and what we can do. But we really need to make the issues of emissions, particularly from the oil and gas industry, which has been mentioned, is capable of reducing emissions dramatically with existing technology, and much of those reductions at no net cost. It truly is low-hanging fruit, to use an overused expression. So the goal was to launch a new low-cost, purpose-built satellite that can map and measure oil and gas methane emissions worldwide. It can complement, and I'll talk about that more, the satellites we've already heard about. This is not a substitute, this is a complement to, and really allow us then to also move out into agriculture and to the other sources of methane, which are important, but they aren't as readily amenable to solutions rapidly, which is critically important. So the mission has a specific goal, which is to ensure that we can reduce, or we do reduce, our methane emissions from the oil and gas production around the globe by 45% by 2025. That's aggressive, but it's completely doable. And I'll show you in a minute why it's so critically important. We need to make these reductions, dramatic reductions, and we need to do them soon. And then many of the things that we will see, we heard about earlier in the Arctic and other sea ice melting, we can slow that rate. We can't prevent it, but we can slow that rate dramatically because we can slow the rate of warming literally over the next couple of decades. That is incredibly important. That can be done in the methane space in a way that CO2 can't, because methane dominates that near-term changes. So our goal, as was mentioned, is to be able to monitor greater than 80% of the regions that are producing greater than 80% of the oil and gas produced globally. To be able to track area emissions. Again, Christian talked about this in his talk about being able to do the full inversions, as well as point sources. So we need to know the specific points, but we also need to know the total. We need to be able to track that over time. It's a sun-synchronous orbit, as we've talked about with other satellites, where we're in production right now. The satellite is largely constructed, and we will be launch ready in the fourth quarter of next year. As an integral part of it, we're going to produce a flux data product. How much methane is being emitted where? Again, Christian showed some wonderful slides of that, and I'll talk about it a little bit more in a moment. All the data, just like we heard about from Copernicus and the ESA, European Space Agency data products, are freely available to the public, and the underlying science data will be freely available to the science community. In addition, we have an advocacy campaign with that to ensure that the data are actionable and in a good place, understood, and will be used by those who can make a difference. Now, I want to talk a little bit about the science, just to be sure, because this is a point that's not fully understood by everyone, and I think it's a critically important one. If we think about when we make these reductions, many people have said, well, we want to get rid of oil and gas in order to decarbonize our economy, which we certainly will need to do. There's disagreements on how quickly that can happen. But if we take a fairly aggressive decarbonization pathway and look at how much methane could be reduced through decarbonization versus a direct mitigation and decarbonization strategy. And if the key is on the right, if we look at near-term direct climate mitigation from the oil and gas industry while we work to decarbonize rapidly, what we see is we can tremendously reduce the increase in warming between now and 2050 than if we only worried about decarbonization. And while for some these may look like relatively small temperature differences, they're huge in the climate world and on the impacts world. I'm a terrestrial ecosystem ecologist. I study the impacts of climate on forests. These are big numbers. These are meaningful numbers for sea ice, for impacts, for effects on storms and heat and droughts. These are big numbers. We have the tools to do it. They will have big impacts over the next couple of years. And as we think about it, we do also have to be careful about our metrics. We can't see these effects if we use CO2e. And I won't spend time now. I'm happy to have a side conversation with folks why CO2e is not wrong, but it gives you a spurious understanding of these kinds of impacts. We have to look at continuous net rate to forcing effects of different kinds of strategies. And then we better understanding of what the near and medium term impacts are versus just the longer term impacts. The mission itself, I'm just going to put up some of the stats for folks. I won't walk through all of them, but the key is this is a really high precision instrument with two spectrometers, oxygen and methane. And as I mentioned at the beginning, it's a purpose-built satellite. We started with a specific objective. How do we quantify methane emissions from oil and gas production globally with the highest level of precision and accuracy possible, with a good repeat time, as previously mentioned, important to keep looking and see how things are changed, how variable they are, and do that at a cost that could be funded through philanthropic means and built relatively quickly. So that was the goal, where it's a combination of using academic science, expertise from the commercial space industry, from the capacity from government space as well, bringing that all together. The satellite is being built by Ball Aerospace, the spectrometers by Ball Aerospace, the bus by Blue Canyon Technologies. Ball is integrating it all, and the primary science teams are at the Smithsonian Astrophysical Observatory, Harvard University, and the Environmental Defense Fund. We also have a partnership with New Zealand government, who will lead the mission's operations portion, the mission operations, will be located in New Zealand. And they also have a large team of scientists that they're putting together that's working on and using methane sat data to understand agricultural methane emissions and how we can use the technology and the data from methane sat to look at agriculture and affect a mitigation in that domain as well. This is just a sense of how we'll target it. It's not a continuous global mapper like Tropomi on the Sentinel-5P. But we will target it. We can slew it so we can see wide swaths as it's going around the world. We will target all of the oil and gas areas of the world, as well as other areas of interest like agriculture and particular targeting. We will also be using predictions of cloud cover, so we won't be just collecting everything. We're collecting when there's a high probability of getting high quality data. It's also important to note, again, as Kairos has been working on, we have a fully integrated, automated inversion system for all the data we're collecting, and it'll be the base product we will share. So unlike, this is a cloud-based system, which as far as we know have never been done. The full system is cloud-based with a full inversion for all the data we collect. So the level 4 data product is what we'll share across the globe for heat maps of methane emissions per unit area, which will allow us to get a quantitative estimate. Concentration data is very interesting, but it's not policy relevant. We can't use it to act on it because the gradients in concentration don't correlate with the underlying concern of emissions when it comes to greenhouse gases. As we said, for some air pollutants, that's of course not the case, where the concentrations are the key variable of interest. So this automated system and the underlying algorithms we've been developing in parallel along with the instrument for many years now, and it will be ready on day one. We have an aircraft, Methane Air, that's flying. It'll be flying again actually in roughly 5 weeks. And we're using the data from the instruments on the airplane, which are comparable to those that'll be in the satellite, to do the algorithm refinements to ensure that we'll have a high quality product on day one. Obviously, it'll need some additional work over the few months following, but it should be in, relatively speaking, good shape so that the time lag between when we can do routine full data products and launch will be relatively short. And as was mentioned, here is some data from Tropomi, which is the instrument that was previously talked about on the Sentinel-5P, a really great instrument that moved us far ahead. You can see the Permian, which Christian talked about, and some of the work there. This was a paper we put out a little over a year ago, working jointly with the folks at Esron, who were responsible for the methane data products off the instrument at Harvard and led by my team at EDF. And taking that concentration data for the Permian Basin, which is by far the largest oil and gas producing region in the US and one of the largest in the world, you see these concentration gradients, but again, that's not actionable. The key is really being able to get the full inversion and be able to see how it varies. This is an 11-month period integrated. What's the total quantity and how it varies spatially? The challenge we have with the Tropomi, which is again an enormously powerful instrument that moved us far ahead, is that the spatial granularity, the pixel size is too large to really individually use that to look at comparisons across actors. We need to be able to think about it in a much more spatially resolved way while totally quantifying emissions. We believe that we'll be able to do that with methane sat, building on what Tropomi's doing, because we won't have daily coverage, but we should have repeat measurements for important areas about roughly every 2 to 3 days. But be able to do this routinely rather than, of course, this work took a lot of concentrated effort by a whole team. We're automating all of that moving forward. Just quickly, we've heard about the mappers like Tropomi. We haven't heard about the target mode instruments like GHGSat or Carbon Mapper, which will be launched 2023. And then Methane Sat, which is really a hybrid. It's looking to maximize the information by doing mapping, but having target capacities. And Sentinel-5 P, and Tropomi has some target mode. Christian showed data, but it's a very high detection threshold. So most of the overwhelming majority of the point sources you can't see with the instrument. You can see that fat tail, which is critically important. And as he said, there's no reason for those kinds of large emissions to occur. There's different types of data. The key here is that we need to make routine that all data is produced for greenhouse gases as a base product of flux rates. That's the policy relevant data. That has to become the new norm. Copernicus is working on that in the integration, but we need to bring it back up the data pipeline so that all of the data is automatically processed as a flux rate, because that is what we ultimately need. And we have to do it we can't do it in real time. There's a delay because of QA/QC, but we need to do it in near real time, produce that data in very short lag times from when we actually see it. The key data characteristics that go into all of this ultimately leads to this detection threshold. What proportion of total emissions can we detect? Again, Christian talked about that. We need to have low detection thresholds. While Tropomi can see a lot of what's being emitted, where it can see it, it can't see emissions from many regions of the world because its detection threshold is too high. Where it can see it, as we showed in the Permian, it's a very powerful tool, though not spatially resolved to the level we ultimately need. So we've moved way forward, but we haven't gotten all the way there to having all the data we need. We have actionable data today, again, as Christian mentioned, but we need even more of that. We need global coverage. We need rapid repeat measurements. We need to be able to detect total emissions. We need to be able to see point sources. We need to be able to see spatial patterns of emissions and these area sources, and we need to track it over time. And we are building an ecosystem across the satellites that we've heard about that together will provide that rich data that allows us for the first time to understand on a global scale total emissions, map them, understand where they're coming from, how they're changing over time, how much is being emitted, and we then have exactly what we need to be able to determine policy objectives and meet them and verify them. Something we've never been able to do before, and we're getting really close to being able to do that moving forward. In the case of methane sat, I just want to highlight a couple of things. Our detection limit will be down around 2 to 5 kilograms per hour per square kilometer. That's more than an order of magnitude lower than anything that currently exists, and a couple of orders of magnitude lower than is generally the case. We will see point sources, but only the larger ones will be a bit better than Tropomi on its good days routinely, but that's what we didn't design it for. For persistent sources, will be considerably better than Tropomi, but not nearly as good as GHG-SAT or Carbon Mapper. There's a gap there. You put the data together, we get a real increased clarity. We'll be able to look at a lot of priority targets on a daily basis in the way that I described. And then just to end, just comparing across this ecosystem of satellites, the capacity is growing. As I said, we have complementarity across mappers and target mode. And what's really exciting is when we put all these data together, we'll be able to see, as I mentioned, understand the picture, understand what's going on, see how it changes over time, and be able to reward those who are doing a good job and point out those who are not. Thank you very much.